Okay, so the idea for today is LU factorization. Right, and so let's just okay. Why is my mouse refusing to? There we go. Okay, so here's the idea. Let's see where this idea comes from. And today we're going to be talking about a special kind of system, which is a triangular system. And that's something that we've already seen, right? Upper triangular and lower triangular, we've seen that once we do Gaussian elimination. So let's take a simple idea. Let's look at a simple system. So this is x plus, so we have x plus 2y is equals to 5, and 4x plus 9y is equals to 21. Right, so that's the system that we have. I'm going to take a little, let me just set up the chat for myself so that I know if there's any question. Okay, so here's what we do. Let's do Gaussian elimination once on this system, and let's see what we find. And this is something that we've done several times, so we should be familiar with what happens. So let's just look at the augmented matrix, perhaps. So we have 521. So this is the augmented matrix, and we're going to focus on this side of the matrix, which is matrix A, right? So when we write this as AX equals B, today I'm going to focus on this, just this left hand side square matrix A, which is 1, 4 and 2, 9. And so let's now do a row operation. And so the row operation that I will need is row 2 minus 4 times row 1. That's the row operation that I want. And so this row operation we've seen can be incorporated using an elimination matrix, right? And that elimination matrix is very simple to build. We've seen that is that if we want to do this row operation, so this row operation is happening in the second row. The first row will be preserved. So the first row is just take one of the, notice each row as taking some linear combination of the rows of the next matrix, right? So we have 1, 2, 5, 4, 9, 21, and I want to multiply it such that the first row is preserved. So think of it as taking linear combination of the rows. So each row will give me a linear combination of the rows. So take one of the first row and take none of the second row. And in the second one, take negative 4 of the first row and 1 the second row. And so now we can multiply these matrices together. I get the first row as it is because that's how I built the left hand side matrix. So this is, let's call this E1, let's call this A, and right, and so this I can now call, so what will happen here? So I will get minus 4 plus 4 is 0, minus 8 plus 9 is just 1, and then minus 20 plus 21 is just 1. So that's the matrix that I've gotten, right? So let's talk about the product. Let's talk about E1 times A. When I just look at this side of the matrix, E1 times A has given me this matrix, right? 1, 2, 0, 1. It has given me a matrix that has 1s on the diagonal. So notice that if I count this as the diagonal, I call this the main diagonal. This matrix only has, well, it has 2 diagonals, 1 main diagonal and 2 off diagonals, and we'll see that in larger matrices, but right now this is just 1 diagonal which has 1s on the diagonal and something above the main diagonal. And so such a matrix is called an upper triangular matrix, right? So that's an upper triangular matrix. So let's call this matrix U. And also notice something else. Notice that this E1 was a lower triangular matrix. It had something on the main diagonal and then something below. everything above the main diagonal was 0. So when you have everything above the main diagonal to be 0, that's a lower triangular matrix, right? Okay, so let's write that matrix equation and let's see what we get. We get E1A is equals to U. Now let's say I want to take this E1 on the other side. So I'm looking for A is equals to E1 inverse U. So I assumed that the inverse, so I did something. I said assume that E1 is invertible, right? We don't know for sure whether the inverse exists or not. This is something that we talked about in the last class, that inverse may or may not exist. But let's now for a moment assume that this the inverse of this simple elimination matrix exists, right? And we will see in a bit that it's very easy to say that the inverse of all elimination matrices actually do exist. And so now let's think about it. Let's not try to find the inverse. Let's try to by computing it, but let's try to reverse what this E1 did. What this E1 did was the row operation row 2 minus 4 times row 1. If I want to reverse this row operation, all I can do is the reverse of that operation will be take U and do row 2 plus 4 times row 1, right? And let's see if that gives me the same matrix, right? So I'm going to guess that E1 inverse is actually the matrix, preserve the first row, take 4 times the first row and add it to once the second row, take the upper triangular matrix which is 1, 2, 0, 1, 1, 2, 0, 1, and now let me compute this matrix product, and this matrix product gives me the following. So let's see what I get. Let's take the simple matrix product. Let's do dot product for row times column, 1, 1. So this is 1. First row of course is preserved, and the second row we take, so 4 times the first row plus 1 times the second row. So 4 times 1 plus 0 is 4, and then 4 times 2 is 8 plus 1 is 9. And now if I check it out, then matrix A was exactly this matrix 1, 2, 4, 9. So I seem to have successfully found the inverse matrix. So this is A. So this was E1. I can say for sure that this was E1 inverse, right? And so now let's look at this product. Let's look at this actually in a little more detail. So what I've done successfully right now for this 2 by 2 matrix is I have written it. This is E1 inverse and this is matrix U. And so what I've managed to do is I've managed to factorize A into the product of a lower and an upper triangular matrix, right? So this is a lower triangular matrix, this is an upper triangular matrix, and for now let me just call this E1 inverse, let's call it L. So this is called A equals to LU, and that's why it's called LU factorization, a lower triangular matrix times an upper triangular matrix, right? And in this case, this lower triangular matrix was just equal to this elimination matrix, but that may not be true, because in this case we only needed one elimination matrix. What happens if we need multiple elimination matrices, right? So what happens if we consider perhaps a 3 by 3 case? So let's talk about a 3 by 3 scenario. So let's look at a system that we perhaps looked at in one of the previous classes, which was 1, 3, 2, 2, 2, 2, 3, 5, 6 times. So now we're looking at a 3 by 3 system, 3 by 3, and we have XYZ is equals to minus 3 minus 2 minus 5, right? Okay. So now let's take this matrix 1, 3, 2, 2, 2, 2 and 3, 5, 6, and let's do the elementary row operation. So I think I remember that from the previous classes we did the following. We did row 2 minus 2 times row 1, and that's easy to see, and we also did row 3 minus 3 times row 1. So the first elimination matrix that we're going to do, the multiplication by is 1 0 0 minus 2 1 0 minus 3 0 1. So that's, oops, let's not build one elimination matrix. Let's preserve the third row in the first case. So this is E, I'm going to call it E21, and this will be multiplied by 1 3 2 2 2 2 and 3 5 6, right? So that's my matrix A. So once I do this elimination, I get the matrix. Let's do the computation. The computation is simple. So I preserve the first row, I preserve the third row, and for the second row I do minus 2 times the first row plus the second row. So 0 minus 6 plus 2, which is minus 4, and minus 4 plus 2 is minus 2. And hopefully I've done that correctly, because I know I make mistakes. Minus 6 plus 2 minus 4, yeah, and minus 4 plus 2 minus 2 seems correct. Hopefully I've done this correctly. And so this was E2, let's call this matrix E21 times A, because now it's not just A, it's the product of these two matrices. And now let's do the next row operation, which was preserve the first row, preserve the second row, but for the third row, minus 3 times the first row and add it to the third row. So let's call this E31. And so now I get the matrix preserve the first row, preserve the second row, and the third row is simply minus 3 plus 3, 0, minus 9 plus 5, minus 4, and minus 6 plus 6, 0. So that's my matrix E31 minus 6 plus 6, yeah, E31, E21, A. And now I need just one more elimination step to get rid of this one, and that I know should simply be row 3 minus row 2, right? Because they are exactly the same, so I just need to subtract them. So I don't need any multiplier, the multiplier will just be 1. So preserve the first row, preserve the second row. For the third row, don't take the first row, take negative 1 times the second row and add it to the third row. So just like that, right? So you must have started noticing that in the elimination matrices, we also get something interesting. We get ones on the main diagonal, right? So again, 1 in the main diagonal. So it's very close to the identity matrix, but there are at least one non-zero entry in the lower triangular matrix, and exactly 1 if you do one row operation with one elimination matrix, right? Okay, so let's call this matrix E32 because row 2 is being added to row 3. And so let's compute the product. And the product is the following. Here's the product. This is E32, E31, E21 times A, which is first row as it is, second row as it is, and the third row 0 minus, so 4 minus 4 is 0, and minus 2 plus 0 is minus 2. And there we go. We finally gotten, after 3 elimination matrices, we've gotten this upper triangular matrix. So let's just call this U. And so my equation becomes E32, E31, E21A is equals to U, right? And now I want to make the same argument. I want to take all of these elimination matrices, right, from this one, all of these elimination matrices on the right hand side. And so I repeat the same step. I say I find the inverse of this one, inverse of this one, inverse of this one, and let's take them on the right hand side. So first I will need to multiply it by E32 inverse on the right hand side, and on the left hand, and from the left hand side, and over here I get E32 inverse U. So that gives me, these two give me the identity matrix. I have E31, E21A is equals to just this E32 inverse U. So I've taken one matrix here and taken its inverse, right? So notice that the order will change. If I had the order first was multiplied by 2 1, 3 1, 3 2, now the order will be exactly in the opposite direction. So you first multiply by the inverse U. So in other words, think of it as row operation. You are reversing the last row operation that you did, and then the second last row operation that you did, and then reversing in the opposite order so that you get exactly the same matrix, right? So let's say I multiply by E31 inverse, then by E21 inverse, and so I finally get the matrix. I'm skipping 2 steps here, but I hope everyone can see what's happening. So I get E21 inverse, E31 inverse, E32 inverse times U. So this gives me the matrix A factorized into a product, right? And now I want to simplify this by noticing one important thing, that all 3 of them are lower triangular matrices. And an important fact is that product of lower triangular matrices gives lower triangular matrices. So I can combine them, and we can even check that, right? So let's take the product E21 and E31. Let's multiply them together, and I know if I want to do both of these row operations together, I would actually get the matrix, the following matrix 1, 0, 0. You can multiply them together and you can check that E31 times E21 is actually equals to minus 210 and minus 301. And we've already done this before, so we've already checked this, right? So, and this matrix, notice this is also lower triangular. And if you now take this matrix and multiply it with this, so then the overall matrix will be 1, 1, 1 on the diagonal, zeros here, and on this one you get minus 2, minus 3, and minus 1. So that's my matrix E32, E2, E31, and E21. So this is just a big lower triangular matrix, right? And so its inverses will also be given by, so let me just write that explicitly if you haven't guessed what the inverses are going to be, right? So the inverses are going to be the following, and let's just write U here. So in reversing this row operation just means take ones on the diagonal. This row operation took negative times the second row and added it to the third row. So I'm just going to change the sign and I'm going to add that, right? So let me just give you one more time what I'm talking about. This E32 had a negative sign here because it was doing R3 minus R2. E32 inverse will do R3 plus R2. So all you need to do is just change this sign from minus to plus. So, and doing that so this is what you get for E32 inverse. And doing that for the other 2 matrices, you get 0 here, 3 here, and 0 here. And for this one, you get 2 here, 0 here, and 0 here. And if you now multiply all of these matrices together, you get the nice little lower triangular matrix, which is 1, 2, 3, 1, 0, 0, 0. And you've gotten this L matrix, this lower triangular matrix, which again gives me the LU factorization of a 3 by 3 matrix, right? So hopefully everyone has absorbed what was going on. So we did the LU factorization, right, of a 2 by 2 matrix and of a 3 by 3 matrix. So now the question is, why did we make this effort, and why not just stick with Gaussian elimination, because that just suits our purposes? And so why do we need to see that this is happening in the background, right? So here's the important thing. Let's talk about why we would want to do LU factorization, right? Actually, what we're doing in Gaussian elimination, suppose we have the LU factorization. Now question is why we are doing this, right? So suppose we have the LU factorization of A, right? So I have some n by n matrix, and I have done the LU factorization. So I have A equals to LU. This is a lower triangular matrix and this is an upper triangular matrix, right? So I have the LU factorization of this version, and now I want to solve, let's say I want to solve the system. So I need to solve AX equals to B, right? Okay, so AX equals to B. Now I can do the following. replace A by the LU factorization of A, LU x equals to P, and at this point make a substitution. Notice that this is an unknown when we try to solve Ax equals to B. This is known. We know what this matrix is. We know what this vector is. And we know what this is. This is also known, right? And so we're assuming that L and U is also something that we know. So we do this substitution. We say, okay, let's take this Ux, right? So if A was n by n, then L and U will also be n by n, which means that U times x, which is n by n times n by 1, will give me a vector. This is actually a n by n vector, right? So, and I don't know what this vector is because x is an unknown, right? So this will be an unknown vector, but let's call that unknown vector y, right? And so remember this, we need this, so remember this for later. But now we make the substitution in Lux equals to B, and what we get is Ly equals to B, right? Now instead of solving Ax equals to B, we're now trying to solve, this is a known system, this is a known vector, we still don't know what this is, but we know what this is, right? So this is known. So now we're trying to solve Ly equals to B, but the great thing about solving Ly equals to B is L is lower triangular, so there's nothing here. So there are some entries, maybe let's say ones, I'm not sure if they'll be ones, but these are all zeros, and let's say there's something here, 2, 3, let's take the one that we already have, and so now this is y1, y2, y3, and I have some right inside, right? So this is b1, b2, b3, okay? And so this system is really easy to solve. We can just solve this using forward substitution. And what's forward substitution? Is just the first equation gives me the value of y1, so y1 is exactly b1. Then I can use the second equation, which tells me 2y1 plus y2 is equals to b2. I already know what y1 is, so just take this on the other side, I get b2 minus 2y1, and I have the value for y2. And so on and so forth. You can do it for all the values that you want. y1, y2, y3 will be known. So y is known. We have solved the system for y using a simple method, which is forward substitution. Okay, but what's the point, right? We didn't need y. The question said that we need to solve Ax equals to b. We want to solve for x. What's the vector x? And now we take the substitution that we did and we use that substitution. So we now go and say, okay, but y was the substitution that we did for ux equals to y, and now this is again another system that we need to solve. This is now known, this is an unknown, this is known, but now again you're solving a triangular system, and triangular systems can just be solved by substitution. So now this is an upper triangular matrix, and you know what upper triangular matrices look like. So there is something here we don't know, so 0, 0, 0, but these entries have some value, right? And so I have x1, x2, x3 is equals to, and we already know what y1, y2, y3 is. So now I can say that x3, whatever this was, let's say 5. So I get 5x3 is equals to y3, so x3 is simply y3 over 5. You simply solve the system using, now the system can be solved using back substitution. Okay, so forward substitution and back substitution. So instead of solving Ax equals to b, we can first solve Ly equals b, and then solve by forward substitution, and then we solve ux equals y by back substitution. So we converted the solution of this system into solving two triangular systems, and triangular systems are nice because they're just easy to solve using back substitution or forward substitution. Now the important question at this point that you should be really asking me is, again, but why did we do this? Because if Gaussian elimination was giving me, if you remember that Gaussian elimination was giving me this upper triangular matrix, and I had already augmented the right hand side, and now I just I could have just used this to solve. Why did I need to store L in the first place? Why need L? The answer to that problem is, what if you needed to solve, what if later you want to solve another system AX is equals to C. So let's suppose you solved AX equals to B, but you didn't store anything, like you just stored the solution. This will have a completely new solution. And for this one, if you solve your system using augmented matrices and by elimination, you're not going to have access to what the C vector will convert to, right? So when you do elimination using a Gaussian elimination process on the augmented matrix, this B1 actually changes, right? So this B changes because you're doing some row operations here. So this B changes into something else. So we don't know what this C will change into once we do all the same Gaussian elimination steps. So, but if we had stored L and U, we can still do the same thing. So if you just factorize it once and you have L and U, you can just do, this time you will be solving Ly equals to C first. So right, so let's say this AX equals to C will be Lux equals to C. We do the same substitution, y is equals to ux. So we do Ly equals to C, we solve that first, and then once we have y, we solve ux equals to y. And that's the same process. You do forward substitution here and backward substitution here. And so the benefit of doing LU factorization is you just need to factorize A once. And then you can do forward substitution and backward substitution on as many right hand sides you want. If you have to solve it for 100 right hand sides, you can do that. You will only need to do one forward substitution and one backward substitution, right? So if you think about it as computational cost, then to solve 100 systems such as AX equals to B1, AX equals to B2, ... AX equals to B100, what we do is we factorize A once into LU. So that's my first cost. So this is my first cost, and the second cost is then solve 100 systems by forward substitution, and then solve another 100 systems by backward substitution. So you'll be doing Ly equals to B1, Ly equals to B2, and so on, and then you will be doing Ux equals to Y for each of these different Ys. So let's call this Y1, Y2. So Ux equals to Y1, Ux equals to Y2, and so on. So you will get all of these X1. So let's call this X1, X2, X3, X100. Then you'll be able to solve for X1, X2, and up until 100. So you'll, at the end of this process, you will get X1 to X100. The important thing is that you need to do this only once, and that's really important, because Gaussian elimination in this entire process, when you're solving this system, when you do something like this, Gaussian elimination takes the most time. It takes the most computation, and it takes the most amount of time. And let's talk about how much computational cost it takes. So what's the cost of elimination? It's the computational cost of elimination. So let's consider a n by n system. Let's say I have this A matrix which has n rows and n columns. Let's talk about what we need to do to eliminate the entries, right? And what we're doing is, so let's say it has some entries A11, A12, up until A1n, A21, A22, A2n, ... AN1, AN2, ANn. right? That's the matrix. So what's the first step of this elimination process? The first step of this elimination process is getting rid of all of these A21, A22 and eliminating all of these, right? So firstly, I eliminate n minus 1 entries. That's the first step. What's the second step? The second step is taking these. When you reach this point, you need to eliminate n minus 2 entries. N minus 2 entries, right? And then you have another, when you reach the third, so in the first column you need to eliminate, so you need to eliminate n minus 1 entries. In the second column you need to eliminate n minus 2 entries, and so on and so forth. These are the entries that you need to eliminate. Okay. Now the question is, what's the cost? So right. So now the question is, how do we eliminate this entry? When we eliminate some entry, so whenever we're eliminating, so let's say eliminating A21, we'll need to do something like row 2 minus something, right? So you multiply something by, let's call this the first multiplier, and minus row 1, right? That's something that you need to do. But notice what you're doing. You're multiplying all of these entries. So you're multiplying all of these entries by something. So the entire row 1 gets multiplied. So you're doing n multiplications. And then you're doing, so this step is n multiplications, and then since this entire row is being this entire row is being subtracted from this entire row, you're doing n subtractions, right? So this n multiplication and n subtraction is happening from one row, which means when you eliminate all of these entries, you're doing n multiplications and n subtractions for n minus 1. So you're doing n multiplications for n minus 1 entries, right? So you get something like n times n minus 1. So let's count this n subtraction and n multiplication as one step. So what you get is essentially you're doing something like n squared minus n operations, right? And let's just keep things simple, because n squared is the bigger term here. We know that polynomials, as n grows larger, n squared is the term that will really dominate this. M squared is going to grow much faster than n. Then let's just approximate this by n squared. So the first step is sort of taking me n squared operations, right? So eliminating all of these gives me n squared operations. That's something that I have to compute for each row. Then in the next step, so this was my pivot, then I find some new pivot here in this position. This A22 will of course change, but now I need to eliminate all of these entries, right? So now I want to eliminate n minus 2 entries, but now something has become easier. What has become easier when I start doing row 3 minus row 1? Well, it's not going to become easier, at least in this step. So this step is still going to cost me about n squared, right? So I'm going to get these n squared operations at least in this. So actually I think I've already talked about this. Sorry, this was not. I've already talked about this one. So these n minus 1 entries, what am I doing? Okay, sorry, I was talking about the elimination. Extremely sorry, I've lost my train of thought. So I'm now talking about eliminating this entry. At this point, all of these are zeros, right? So I was doing row 3 minus some multiplier, let's call this multiplier m2, and this being multiplied by row 2. The important thing to notice at this point is that if this is row 2 and if this is row 3, then the first entries of these are already 0. And so what I'm going to do now, the multiplications and the subtractions that are going to happen, they're not, in the previous one there was n multiplications and n subtraction. In this one, I will have n minus 1 multiplications and n minus 1 subtraction. So let's just approximate that by, so I'm going to do this n minus 1 and I'm going to do it for all of these n minus 2 entries, so I'll get something like n minus 1 squared operations, right? That's something that I will get. So now the idea is when you start eliminating these entries, so this first column costs me about n squared, this second column costs me about n minus 1 squared, and so the idea is approximately when I add up all of these operations, I get n squared plus n minus 1 squared plus n minus so on dot 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 plus 1 squared. So I'm getting a sum of squared, which in our case is going to be, if you add up the sum of squares, if you use the sum of squares formula, you get something like 1 upon 3 n plus half n plus 1 upon 3. You can check, you can do this computation on your own. You can use the sum of squared formula if you want. You can just individually check. It takes a little bit of thinking, but it's not impossible to figure out why this formula is true. But what I want you to focus on is that the dominating term of this entire formula is the n cubed term, right? So when you multiply, this is a linear term, linear term, linear term. This is a cubic polynomial which has been factorized into 3 linear polynomials, and the dominating term will of course be the n cubed term, right? The highest power term is the dominating term, which is 1 upon 3 n cubed, and that's the cost of Gaussian elimination, n cubed, which is high, a very high price to pay. And the reason it's a high price to pay is, well, if my n was 100 by 100 systems, I'm doing about 1 upon 300 cubed operations, and this immediately gives me about what, 100, and gives me what, 1 million operations. So let's 1/3 of a million operations. And you can easily see that this cube is going to become a real problem if I just add one more zero. I went from a million computation, I increased the order by 1, went from 100 to 1000, and I see that I will need 1/3 of a billion operations, which easily, and 1000 by 1000 system is nothing in this age. We have data sets that have, if you are doing Gaussian elimination perhaps to solve a data system problem, and you have a large system, this cost is nothing, right? And so if anything that cuts down the cost of Gaussian elimination, so if you want to solve ax1 equals to b1 and ax2 equals to b2, and your plan is to do Gaussian elimination on this and then Gaussian elimination again on this, you're going to incur this cost twice. The smart thing to do is do Gaussian elimination just once. So you pay the price, but you don't keep on paying the price. You do Gaussian elimination once, and you incur the cost, and then store L and U. You do, by Gaussian elimination, you find what L and U are going to be, and instead of, so let's give this a new name. Instead of doing Gaussian elimination, what you're doing is you're doing LU factorization. It's exactly the same process, but we're just giving it a new name. So do LU factorization once, it has exactly the same cost, but now instead of paying that cost over and over again, what you need to do is you can solve by forward substitution and by backward substitution. And if you think about it, I think I'll leave this problem for you to think about, that the cost of a forward substitution is about the order of n squared, and the cost of n squared, and the cost of a backward substitution is also about the order of n squared. So this is nicer. You won't have to pay 1/3 of a billion. You will just have to pay about, if you have n equals to 1000, then from a billion you went down to at least a million. So you get something like this, and you can pay this cost twice and it still won't be. So you're doing forward substitution and backward substitution. 2n squared is still always going to be, well, not always, but it's going to be, for larger systems, for n large, I can almost guarantee you that 2n squared is definitely going to be less than n cubed upon 3. And you can figure out, actually this is a nice little inequality which you can solve. You can solve for which n, actually. For which n? How large is n? You can solve this inequality and see at what n my LU factorization becomes the right step to go. So that was a lot about LU factorization. I'm going to add one more bit to this. Let me just take my LU factorization that I had. I did it for a system, right? So here's my L, and where's the U matrix? So this was the U matrix. Let's take this matrix. This is something that I want. Oops. Let's bring this down here. Copy pasting is nice. You don't get to do that on the whiteboard, do you? That's one silver lining of all this, I suppose. You get to copy paste, and you don't have to erase the notes on the board, you just have access to them. Okay, so here's the, so let me just put this right here, and instead of using, let me just erase this U. There we go, that's the A is equals to some L matrix times some U matrix. Okay, so here's what I wanted to talk about. I wanted to talk about the diagonals of L and of U. By construction, the way we construct the elimination matrices, the main diagonal of L is going to be 1s always. That's true because whenever we build E21 or E12, I know that the row that we're dealing with is always 1. If you want to add something to row 2, you put something here, right, some entry here, but you keep row 2 as it is. So row operations always look like row 2 minus something row 1, row 3 minus something row 2, or row m minus something row n, right? Notice that the factor here is always 1, right? That's how we do it, that's how we set this up, and that's the reason we always get 1s on the main diagonal. So L will always have 1s on the main diagonal, but U on the other hand can have 1s on the main diagonal. Sometimes it might, sometimes it won't, right? So notice that I think in the first system that we solved, which was I think this 2x2 system, yeah, here we go, in this case it turned out that we have 1s on the main diagonal, but in the 3x3 system that we solved, we didn't get that. And so we're not guaranteed always, like we were guaranteed in the case of L, that the main diagonal would be 1. So that's something that we can actually fix by taking these diagonals. So if I divide this second row by -4, then I can get 1 here. If I divide this third row by -2, I can get that row. So let's try to do that, shall we? Let's say I put a matrix in the middle, and I'm going to do something like this, so 2 1 3 1 1, and so I'm going to do this division, right? So I want to divide by -4 in the first case and divide by -2 in the third row. So I'm going to divide, I'm going to put a matrix here that divides the the U matrix 1 3 2, and if I can do this division over here, then I get 0 1 here and 0 0 1 here. So this is, I put 1 here because I don't need to change the first pivot, 0 0, preserve the first row, put -4 here and put -2 here, right? So that's what I want. And what I want is when I multiply these two together, I get this, right? So this is what I want. So this, let's call this matrix T, and let's call this, for now let's call it U star. So T times U star, I want T times U star to give me matrix U. And I'm going to do this division, and I've done it in a way that when I multiply this, so notice what this row does. This row does nothing to the first row, takes -4 times the second row, which means I've if I've divided the second row by -4, then this is, if it's going to multiply by again by -4, then I need to change this entry, because if I just keep this as 2, let's see what happens. If I just take this entry and plug this here, that won't give me the right result, because the resultant matrix that I will get is 1, 3, 2, and so this one takes 0, this one becomes minus 4, which is correct. That's the entry that I wanted. But now if I multiply minus 4 by 2, I get minus 8 here, and that's a problem. That's wrong. I wanted the entry here to be 2, which means to fix that problem I need to divide this 2 by minus 4. So if I can take this, if I can make this 2 by minus 4, then when I multiply minus 4 by 2 by minus 4, it becomes just 2. So minus 4 and minus 4 cancel out, it becomes 2. So I change this entry to 2 by minus 1 upon 4 with 2 divided by minus 1 upon 4, which is basically 1 upon 2. And notice now that when you do the multiplication, minus 4 times minus half gives me, so minus minus plus, and that gives me 2. And of course you don't need to change anything here because it's just this entry that's going to change. So this is 0, 0 minus 2, right? So, and now the nice thing is that I've got 1s on the main diagonal in L, 1s on the main diagonal in U star, and at this point we do some cheating and we say A equals to LDU. In actuality it's the U star, but when it's written A equals to LDU, you're assuming that this U is the one with ones, so one with, or rather the upper triangular matrix with ones on the main diagonal, right? So we're taking this LU factorization one step forward, and we're saying that instead of A equals to LU, we're doing A equals to LDU, so which is exactly the same. This diagonal matrix, by the way, is not going to complicate matters because it's just the identity matrix multiplied by some scalars, right? So this is just going to give us the same matrix, but each of the rows will be multiplied by some entry. So this row will be multiplied by 1, this row will be multiplied by minus 4, this row will be multiplied by minus 2. And that's what the diagonal matrix gives you. So nice little matrix, doesn't change much and doesn't complicate things further. But now we have at least some sort of symmetry. So that was LU factorization. Let's talk about something else now. Talked a lot about factorization, talked a lot about elimination. Let's move on and let's talk about something else. Okay. So the next topic, the next kind of matrices that we're going to deal with are transpose matrices. Right. Okay, so what's the transpose? The transpose matrix is simply, in sort of heuristic terms, not a mathematical definition, flip the matrix along the main diagonal. Okay, and this is the sort of, at least the rudimentary definition of the transpose that we're going to deal with right now. So far we were talking about in LU factorization, and then we were talking about n by n matrices, but transposes don't just exist for n by n matrices. You can have the transpose of a rectangular matrix as well. So let's just talk about, first let's look at a square matrix. So 1, 2, 3, 4. If I call this the main diagonal, and if I flip the values across the main diagonal, so the idea is you swap the values that are here and you swap the values, these values on the upper, the values above the main diagonal come below the main diagonal, and the values below the main diagonal go there. So A transpose is going to be 1, 4 as it is, 3 swaps with 2. Okay, if you look at a 3 by 3 matrix, let's say a 1, 2, 3, 4, 5, 6, 7, 8, 9, then the A transpose matrix, again, you take the main diagonal and you flip along that. So that's the flip that we're going to do. So 2 and 4 are going to exchange places. 1, 5, 9 main diagonal remains preserved. 2 and 4 will exchange places, so 4, 2. 3 and 7 will exchange places, 7, 3, and 6 and 8 will preserve. will swap places. Okay, and another way, now if you're noticing this, another way you can think about the transpose is that notice what the rows of A matrix were. The rows were 1, 2, 3, 4. The columns of A transpose are 1, 2, 3, 4. So sort of you can also say the rows become the columns. Or in other words, you can also say that the columns become the rows. So what were the columns of A? In this case, they were 147, 258, 369. The first column was 147. The first row is now 147. The second column was 258, the second row. And this actually becomes a nice little definition to take the transpose of a matrix which is not square. So 1, 2, 3, 4, 5, 6. Now to transpose this, I need to sort of again do the main diagonal flip, but now notice that don't have a main diagonal, like at least not a nice diagonal around which everything was symmetric. Is a main diagonal has only 2 entries, right? But if we follow this definition of becoming the rows becoming the columns and the columns becoming the rows, then A transpose becomes. So now I want to swap the rows. So the row was the row had 3 entries now, so each column will have 3 entries. So this was a 2 by 3 matrix. Now it becomes a 3 by 2 matrix. So the first row was 1, 2, 3. So now the first column is 1, 2, 3. And the first row, the second row was 4, 5, 6. The second column will be 4, 5, 6. Okay, so that's the transpose of a matrix. And let's discuss some of the properties of transposes. So properties of transpose. The nice thing is that if you're adding 2 matrices and then finding the transpose of that matrix, it's the same as just doing A transpose plus B transpose, as long as the matrices can be added together. So if this is an m by n matrix, this is a m by n matrix, right? So for addition, they need to be of exactly the same size, same rows, same columns. So for example, if I do 1, 0, 0, 1, 2, 3 and add it to 2, 2, 2 and 3, 3, 3, right? The result that I get is 3, 2, 2 and 4, 5, 6. And now if I transpose this, so this is A plus B, right? So A plus B transpose. If I now want to transpose this, then this is simply 3, 4, 2, 5, 2, 6. So this is A plus B whole transpose. So you first do the addition, then do the transpose. And this law is telling me it doesn't matter. You can take the transpose first and then do the addition. So I take the transpose first, which is 1, 0, 0 and 1, 2, 3, and then add it to 2, 2, 2, 3, 3, 3, and you notice you get exactly the same thing. 3, 2, 2, 4, 5, 6. So doesn't matter if you do addition first or transpose first. I noticed that there is a question down here. I will answer your matrix question after I'm done with the transposes, okay? Don't worry about it. The G matrix is actually very simple. You're just writing down all the divisions. I'll talk about it. Okay, the second fact, so that was the first fact about the transpose, right? So that's the first fact. The second fact about the transpose is, okay, what about A, B transpose? What about the transpose of a product? And that's slightly different. It's not the same as just taking A transpose, B transpose. This one becomes B transpose times A transpose, right? So that's the important fact. And you can read why this is so in a book. You can find many explanations of it. I actually don't want to go into much detail, but the key idea is this. The key idea is the following, is that if I take AX, right, so this is a matrix, so let's say this is some n by n matrix, and this is some vector, so this is matrix, and this is some vector. then the transpose of this matrix vector multiplication is simply X transpose A transpose, right? And so you multiply this row, now this is a row vector being multiplied by the column vector, and the reason is when you're doing A times X, you are taking the linear combinations of columns of A, right? But when you're doing X times A, you are taking the linear combinations of rows of A. But if I take X times A transpose, then that's taking the linear combination of the rows of, so let me write the rows of A transpose, but the rows of A transpose are going to be the columns of A So that means that tells us that AX, so now notice that this can't be X, this can't be a column vector now, because to multiply from the left hand side, if this is again n by 1 and this is n by 1 and n by n, I can't do this because this is not compatible, so I have to take the transpose of this vector, right? So X transpose, so the reason is that when you take A times X, that the linear combination of the columns of A, that's the same as taking X transpose times A transpose, which is the linear combination of the rows of A transpose. And the rows of A transpose, because that's how we defined A transpose, right? The rows becomes the column. So if I have, and the columns become the rows, so the columns of A are the rows of A transpose. So we have a nice little fact that AX, that's the key idea, that AX is the same as X transpose A transpose, right? So AX transpose is the same as X transpose A transpose. So it's the same thing but just flipped. This is a column vector, this is a row vector. And so the idea is, now here's the idea, is that if you view AB, right, if I view this as, let's say this is my matrix A, and I write B as some column vectors, right? So this is column 1, column 2, and column n. Then we've seen that we can just view it as AX1. So the first column is AX1, the second column becomes AX2, and so on AXN. That's the matrix A times B, right? And now if I want to transpose this, so let's transpose A times B. If I want to transpose this, then this becomes AX1, AX2, AXN, right? These were the columns, and now I want to take the transpose of this column, right? This matrix. What happens is that the columns becomes the rows, right? So the columns, how do the columns become rows? We have AB transpose becoming, this becomes AX1 transpose, AX2 transpose, and so on up until AXN transpose, which is nothing but, so what is this fact we already discussed, right? So AX transpose is simply X transpose A transposed. So this is X transpose A, X1 transpose A, X2 transpose A, and so on, XN transpose A. And the last bit that I'm going to leave to you, so this is what we got, right? This is what we got for AB transpose. So these are now the new rows of AB. So this is AB transpose, and I want you to check that you can get the same notation for B transpose, A transpose. Is that when you, so view it exactly like this. So this is A, this is B, right? Now view this as what in this same format. Try writing B transpose A transpose and see what you get, right? So these columns, I'm giving you a hint, these columns will become rows, X1 transpose, X2 transpose, and you will have some, this just leave it as A transpose and see what you get, right? Okay. So that was about the product. So the important fact is, you can check out, you can try to do it. If you don't figure it out, if you're unable to figure it out, let me know and I will explain it to you. So this is B transpose A transpose. That's something that you need to remember. Okay, and finally the third important fact is, what about the transpose of the inverse, right? What's the transpose of A inverse? So let's say I have A and I found A inverse. What's A inverse transpose? And that's a nice little property, is that if you take the inverse of a matrix and then transpose it, it's the same if you first transpose the matrix and then invert it. So A inverse transpose is the same. So let's say if you found A's inverse and you took AT and you found AT inverse, the relationship between these two matrices is that the transpose of this is equals to this. So what the reason is, you can get it by a simple transpose. So the idea is, if you take A inverse and you transpose it, you get the inverse of A transpose. That's what the equation is saying. Okay, and this is of course slightly tricky to prove, but maybe we can look at it from this. So if I have A inverse and if I do some transpose here, now notice that at this point we have sort of limited ourselves to n by n matrices, right? Okay, and so inverse is only for n by n matrices. So what do I get? I get, using the previous law, I get A inverse transpose times A transpose, right? So this is something we get, that the A transpose, the inverse of A transpose is the same. So this equation is telling me that the inverse, so if I consider this, okay, let's talk about this, let's in a different way so that it's clearer. Let's call this B and let's call this B inverse, right? If B is a matrix, then only its inverse, multiplying it by its inverse, will give me the identity matrix, which means B inverse is equals to A inverse transpose, right? And what was B itself? B itself was A transpose. So A transpose inverse is A inverse transpose, right? And so this also tells me something interesting, that the transpose A transpose inverse exists, or in other words, A transpose is invertible if and only if A is invertible, which means if the inverse of A exists, then we know for sure that the inverse of A transpose also exists. So A inverse exists. This is an equivalent condition. All right. Let's look at symmetric matrices. What's a symmetric matrix? These are nice little matrices and have some nice properties, and they'll actually be very useful later on. So a symmetric matrix is a matrix where A transpose is equal to A. That is, if you transpose it, you get the same thing. Now, the important thing is it can't be an m by n. So a symmetric matrix will always be square, right? Because if this is m by n, then this is n by m, and then they can't be equal. So they need to be n by n matrices. Okay, let's look at a symmetric matrix. So let's say 1, 1, 5, 9. We know diagonals don't change, right? So if this is 2, 3 and this is 6, then if it's symmetric, then the transpose, the values that they're swapped by will be exactly the same. So 2, this becomes 2, there's 3 over here, and this 6 over here. This is a symmetric matrix. If this is A, then A transpose is exactly the same. If the rows become columns, that's because the rows and the columns are exactly the same. So the first row is the same as first column, second row, second column, third row, third column. They're exactly the same. So A transpose is 1, 2, 3. I can just look at the first matrix and write that down. 3, 6, 9. Right? That's a symmetric matrix. Okay, that's the first thing. Here's a interesting thing. Try taking any matrix. Let's say I take 1, 2, 3, 4, 5, 6. Now this can't be a symmetric matrix, right? Because of course this is a 2 by 3 matrix. It's not symmetric. So A is not symmetric. I know. Let's say A is m by n. It's not symmetric. Let's take its transpose, A transpose. So this is A transpose. What's A transpose now? It's 1, 4, 2, 5, 3, 6, right? So 1, 2, 3, 4, 5, 6. That's A transpose. Let's compute the product. So this is 2 by 3, this is 3 by 2. I am allowed to find A times A transpose. I can do this because the columns and the rows are compatible. So let's find that. A into A transpose, let's see what that gives me. So it's going to be 2 by 2 matrix, I can see that, right? So this is a 2 by 2 matrix. What's the entry? So row times column. So 1 plus 4 plus 9, that gives me 14. Then 4 plus 10, 14, plus 18 gives me 32. And now notice this row times this column is going to be the same as this row times this column, right? You see that? So 1, 2, 3 with 4, 5, 6 is the same as 4, 5, 6 with this 1, 2, 3. I'm going to get exactly the same result. That's going to be 32 here, right? 4 times 1 plus 5 times 2, 14 plus 18, 32. And then finally, 4 times 4, this result is going to be different. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 4, 5, 6. This is going to be different. So 4 squared, which is 16, plus 25, which gives me what? 41. And then 41 plus 6 times 6, which is 36, gives me what? 77. So this is 77. Notice something interesting. This is now a symmetric matrix. And the reason it's symmetric is because when we did this inner multiplication, this 1, 2, 3 with this 4, 5, 6, and this 4, 5, 6 with this 1, 2, 3, we got exactly the same result, 4, 5, 6, because the same numbers were being multiplied. So the idea is that A times A transpose is symmetric, regardless of what A is, even if it's not an n by n matrix, right? Okay, but let's go one step further. Let's check A transpose times A. What do we get? So A transpose was 1, 2, 3, 4, 5, 6, and A was 1, 2, 3, 4, 5, 6. And let's try to do this multiplication. What do we get here? Okay, now I know that this was 2 by 2, 3 by 2, and this was 2 by 3. The resultant matrix is going to be a 3 by 3 matrix, okay? And let's do a row operation. So first time, 1 time the first row and 4 times the second row. So I can say the first row is going to be 1 times this plus 4 times this. So 1 plus 16 is going to be 17. 2 plus 20 is going to be 22. So let me just put in this 1, 4 with 1, 4, 1, 4 with 2, 5, and 1, 5. Let's put 1, 4 with 3, 6, right? And I'm putting in different colors because I have a feeling that I'm going to get this 1, 4 with 1, 4 and 1, 4 with 2, 5 again at some point, right? Okay, so I'm just preparing myself for that. So 1 times 3 is 3, 4 times 6 is 24, so 3, 24 is 27. Okay. And now let's go to this one. So 2 times 5 and 1 times 4. That's something that I've already done. 1 times 4, 2 times 5 was this green result. So 2 times 5 with 1 times 4. Okay, let me do this. So this was the green result, this was the pink result. I'm color coding this so that it's easier. So now I notice that this green result is something that I'm going to get here. Okay, so let's write that down. This result is going to be 2 times 5 with 1 times 4. That's going to be 22. So let's write that down here. But the rest of them are going to be new. 2 times 5 with 2 times 5. I've not done that before, and I probably won't be doing that again. So that's 2 times 2, 4. 4 plus 25 is 29. Okay, I'm not going to color code this because this is sort of useless. Okay. And 2 times 3 is 6, plus 5 times 6 is 30, so I get 36 here. Okay, let's color code this one at least. So 2 times 5 with 3 times 6 is something that I'm going to get at some point again, right? Okay, next result is 3 times 6 with 1 times 4, and 1, 4 with 3, 6 is already something that we've done in pink here, so 3 times 6 with 1 times 4 is something that we've done. That result is here. Then notice that it is exactly where I would have wanted it to be, right here. So 27 is over here, and I'm getting a feeling that I'm about to get this yellow result, and the yellow result was 3 times 6. I have to do with 2, 5, which was something that I did just a few seconds before, right? 2 times 5, 3 times 6, and 3, 6, and 2, 5. So 3 times 2, 6 times 5, I get the same result. This right here, plug it in, and so this is 36. And then finally the main diagonal can be anything it wants, because the main diagonal doesn't really contribute to symmetric nature of the matrix, right? So 3 times 3 is 9, 6 times 6 is 36, and I get 40. And so this you can, exactly because of the color coding, right? Let's forget at least the colors on this one, right? And you notice that other than the main diagonal, the colors match up and the numbers match up, which means this A transpose, this is a nice little A transpose A, is symmetric. So A times A transpose is symmetric, but it's a 2 by 2 matrix, right? And A transpose A is symmetric, but it's a 3 by 3 matrix. So A transpose A, they're of course not going to be, A transpose A is not in general going to be A transpose, even if n by n, even if A is n by n. In general, you won't get this result, right? You can try it out with the 2 by 2 matrix. You probably won't get the result that A transpose A is equals to A transpose. In this case, it's extremely easy because they don't even have they either won't have same dimension for an m by n case, same dimension, and even for n by n, they are usually not the same. Okay, so that's something that is fine. You don't expect to get it either. It's not something that we're going to worry about. Okay, so that's symmetric matrices. Okay, here's the question. What happens if we try, so I'm combining two topics that we've done today. We've done LU factorization and we've done symmetric matrices, right? What happens if we try to do LU factorization on a symmetric matrix? What happens here? Okay, and I think I'm going to use this opportunity to answer Danya's question. Danya's question was, she didn't fully understand how the D matrix arrived and how we found that D matrix. So let's use this as another opportunity to find the D matrix. Okay, so let's take the matrix that we had. Okay, so let's take the matrix that we were using before and let's change it a bit for our purposes. Where is it? And I lost it. So A matrix was this matrix. Here we go, finally found it. This was matrix A. Let's bring it right here, and now let's do the LU factorization on this matrix. Okay, now this is not symmetric, so I need to change it a bit to suit my needs. So I'm going to change this entry to 2. I'm going to change this entry to 3, so I make it symmetric, and I'm going to change this entry to 5. Okay, so this was matrix A, and now I'm about to do LU factorization, right? So I'm going to multiply it by some elimination matrix, so I know the first one is going to be row 2 minus row 1. Sorry, row 2 minus 2 times row 1. Okay. Alright, so the matrix for that I know is going to be row 2 minus 2 times row 1, 1, 1, 1, 0, 0, 0, and this is going to be minus 2, 0, 0. Preserve the first row, preserve the third row, and do this multiplication. So 1, 2, 3, 2, 2, 5, and 3, 5, 6. Okay, that's the first step. Let's do it. Let's find out what this matrix is going to be. This matrix is going to be 1, 2, 3, and let's do this elimination step. So this elimination step gives me 0, minus 2 times this, so minus 4 plus 2, which is minus 2, I believe, and minus 6 plus 5 gives me minus 1, so trying to be very careful here so that I don't mess this up. So this is 3, 5, 6. Okay, so this was row 2 minus 2 times row 1. The next step that I'm going to do is row 3 minus 3 times row 1. So now let's build the elimination matrix for that. This is 1, 1, 1, 0, 0, 0, 0 here, negative 3 here, and 0 here. Okay. Alright, so what matrix am I going to get now? So this is 1, 2, 3, 0, minus 2, minus 1, and now 3 minus 3 plus 3, 0, minus 6 plus 5 is minus 1, and then minus 9 plus 6, minus 9 plus 6 gives me minus 3. Okay, good. Now let's do this elimination. Let's get rid of this elimination. Let's take this. So this was the first pivot that we found. This was the second pivot, and now we can use this pivot. And so this becomes, let's see, I preserve the first row, I preserve the second row. For the third row, what I want to do is I want to take row 3. So row 3 is already minus 1, and I want to subtract something, and I want to multiply minus 2 with something so that I can do this, right? So what will I need to multiply with row 2 so that I can do minus 1 minus something and I get 0? So I know that this needs to be minus 1 plus 1, right? So to get plus 1 here, I already have a negative sign, so I don't need to put any more negative signs here, and I can just put a half here. So row 3 minus half times row 2 should do the trick for me. Okay, I'll just leave this here so you know how I got it, and you can rewind the video if you. So 0, you take the ones on the main diagonal, and for this one I'm going to take minus half times this, right? And so the result that the final upper triangular matrix that I get is the following. So this is, okay, so this is 1, 2, 3, preserve the first row, preserve the second row, and now let's look at what happens to the third row. So 0, 0 is fine, minus half times minus 2, negative negative gives me a plus, 2 and 2 cancel, gives me a plus 1, plus 1 minus 1 gives me a 0. That's a success. The other entry is minus 3 plus, sorry, minus, was it a minus here? Sorry, yeah, it was a minus here, right? So minus 3 minus half times a negative 1, right? Am I doing this correctly? So this was minus 1 minus half times minus 2, yeah, I'm doing this correctly. Okay, so this one gives me minus 3 plus half, which gives me what? Minus 5 upon 2, I believe. So minus 6 plus 1 upon 2, minus 5 upon 2. So this entry is minus 5 upon 2. Okay. So at this point, I am ready to say that this is my U matrix. Question: what is L? How do I find L? I need to reverse all the elimination steps. So here's my elimination matrices. This elimination matrix, this elimination matrix, I'm going to combine them together. Okay, I'm going to, these are the 3 elimination matrices. So let's call this E31, E32, E31, and E21. And now I know that L is going to be in the other order. L is going to be the E21 inverse. So this product is E32 times E31 times E21, and L is going to be actually the inverse of these steps, and you can rewind the video if you don't know why this is happening, and E32 inverse, right? And so let's try to do that. Let's try to find what this is going to be. First, let's try to put them all together. We can just put all of these 3 matrices together. You multiply the product, and that's going to be 1, 1, 1. Zeros here. This is going to be a lower triangular matrix with minus 2, minus 3, and minus half. And if I call this matrix E, then the inverse of that matrix, I know that to reverse these row operations, all I need to do is change these signs. If I change these signs, the row operations will be inversed. So 0, 0, 0. This is 2, this is 3, this is half. So L, my friends, has become Okay, so L is equals to the inverse, right? So now L is equals to E inverse, and so this is L matrix. So A is equals to L times U, and the matrix L has become this matrix. So 1 0 0 2 1, 1 0 0 2 1 0, and this was 3 half 1, 3 half 1, and the matrix U is actually this matrix that we found here. Let's copy and paste this. Right here. Okay. Okay. So this is ALU. A equals to LU. And I'm going to do something that's going to give me a nice little property. So this is LU. Let's try to find A equals to L du, and at this point, Dania, pay attention. To get the matrix T, all you need to do is take these pivot entries and put them in the diagonal, right? That's the first thing that you do. The first thing that you do to find D, you leave L unchanged, 1 0 0, 2 1 0, 3 half 1. For matrix D, you take this the pivot entries and you put them on the main diagonal. So 1 minus 2, the pivot entries come from this matrix U, right? So 1 minus 2 minus 5 and 1, 3. You put them on the diagonal, and that's it. That's just matrix T. And to find the new matrix U, so remember U is not going to be the same. U is, if U, this is going to be the new matrix U star, so du star should give us, it will be built in a way such that du star should give me U. And the way we find U star is just to divide each of the rows with what we're getting here, right? So first row will be divided by 1, so that's just 1 2 3, it's divided by 1. The second row of U will be divided by minus 2, so if I divide this, it's 0, minus 2 divided by minus 2 is 1, minus 1 divided by minus 2 is half. So I'm just dividing the entire row by this diagonal entry, because I know when I multiply this together, this minus 2 will be multiplied with this row. So divide right now so that you can multiply afterwards. And finally this becomes 0 0 1. Okay, and let's notice what just happened. If you do this A equals to L du star factorization, and I'm going to do cheating again, I'm just going to call this L du, so that, and you should know that this is just ones on the diagonal. That's the matrix that I'm talking about. I'm actually talking about U star, right? Notice what's different, what's interesting here. Focus on L and U. Same entries, 1 1 2 2 3 3 half half 1. This is a lower triangular matrix, this is an upper triangular matrix. What's the relationship? It's a very simple relationship. It has the same entries, but the columns of L have become the rows of U star. And so actually what we have is A equals to L D. This matrix U is actually nothing but the transpose of L. That's the nice little property that we get. This is what we get when we do LU factorization. The reason that we got this, by the way, is we did LU factorization on a special matrix. This is not always going to be true. We did an LU factorization first, in which we did not get this relation. We only get this relationship when we do LU factorization on a special matrix, which is the symmetric matrix. So I can say that for if A transpose is equals to A, that is if A is a symmetric matrix, then I will have A equals to, I can factorize A into L times D times L transpose. And this is really nice, because not only is this going to cut your time of elimination into half, you don't need to, once you figure out what the lower triangular matrix is going to be, I don't even need to do the multiplication at that point. I just know that they're going to be, I can just keep track of the diagonal entries. At this point, I could have just, I know what's going to be these entries. At the end, I can figure out these entries myself. I just need to keep track of the diagonal and of the lower triangular matrix. So if you just keep track of this So for example, if you just do LU factorization on this lower triangular matrix, that's all you need to do. Okay, so this is a nice little property that we get when we do LU factorization on a lower triangular matrix. Okay, that's it for today. I think I've covered all of what I needed to cover. Yeah, I think I'm going to end the class right here. Dania, did you figure out, were you able to follow where this D is coming from? The important thing is the D is just the diagonal entries of U, right? And U star comes from dividing U by its diagonals, dividing rows of U by its diagonals. Okay, perfect. So let's end this class right here. Thank you everyone for attending. I will try to fix the order of these notes because I know that it's become messed up a bit. Okay, thanks everyone. Have a good day.